The mystery begins with a question that unsettles the calm picture many people carry of Earth's deep past. Why did a planet that had spent millions of years in relatively gentle rhythms suddenly harden, cool, and lock itself into vast grinding ice ages around 3 million years ago, a shift so profound that it still controls the rise and fall of ice today? For most of Earth's history before that moment, ice came and went, but it did so politely, as if respecting invisible boundaries, retreating when warmth returned, and never quite taking full control of the continents. Yet something changed when the Pliocene era was drawing to a close, something subtle enough to leave no single scar in the rocks, yet powerful enough to rewrite the planet's long-term behavior. This story follows how slow planetary forces, almost unnoticeable in any single lifetime, aligned in a rare way, turning Earth from a world of modest seasonal cold into one capable of sustaining immense ice sheets for tens of thousands of years at a time, reshaping oceans, landscapes, and even the evolutionary path of life, including our own lineage. To understand why this change was so shocking, it helps to imagine Earth before the shift not as a frozen world, but as a planet that, while cooler than the age of dinosaurs, still felt surprisingly familiar in many places, with forests reaching far north, seas that circulated warmth efficiently, and ice that rarely overstayed its welcome. Around 5 million years ago, global temperatures were only slightly cooler than today. Carbon dioxide levels were higher, and although Antarctica already carried a massive ice sheet, the Northern Hemisphere remained largely free of permanent continental ice, experiencing only seasonal snow and small mountain glaciers. The Arctic Ocean was not yet capped by thick year-round ice, and Greenland, now synonymous with ice, supported forests and tundra rather than a continent-smothering glacier, a reminder that the frozen images we associate with the poles are not Earth's default condition. Yet beneath this relatively mild surface, forces were gathering with the patience of geology, not in the form of sudden volcanic winters or asteroid impacts, but through slow rearrangements of atmosphere, ocean, and orbit that quietly nudged the planet toward a tipping point. Earth's climate system is not a simple thermostat that responds instantly to change. It is more like a vast network of feedbacks, where small shifts can accumulate, amplify, and eventually cross thresholds that make returning to the old state difficult or impossible. By about 3 million years ago, these thresholds were approached from multiple directions at once, creating a convergence that transformed temporary cooling into something far more permanent. One of the most unsettling aspects of this mystery is how ordinary the causes appear when viewed individually, because none of them seem dramatic enough on their own to explain the birth of mega ice ages. Earth's orbit was changing, but it always does. Mountains were rising, but that too is constant in geological time. Carbon dioxide was declining, but slowly, without any sudden collapse. The shock comes not from any single factor, but from their synchronization, like multiple quiet clocks striking the same hour. This first section opens the door to a deeper truth about Earth's history, one that resists the human preference for sudden events and clear villains, because the planet's most powerful transformations often emerge from patience rather than violence. The onset of mega ice ages was not an accident, nor was it inevitable from the beginning of time. It was a choice made gradually by Earth's systems as they interacted over millions of years. Once that choice was made, the consequences echoed forward, shaping coastlines, carving valleys, and setting the environmental stage upon which early humans would eventually appear. As the climate cooled and ice began to gain a stronger foothold, Earth crossed into a new mode of operation, one where ice sheets could grow large enough to influence global sea levels, atmospheric circulation, and even the chemistry of the oceans. This was not merely a colder version of the past, but a fundamentally different climate regime, governed by longer cycles and harsher extremes. The transition was slow enough that no creature living through it could have perceived the full change, yet fast enough in geological terms to stand out as a sharp bend in Earth's climate history. The mystery deepens when we realize that once Earth entered this icy mode, it never truly left. Even during warm intervals when glaciers retreated and forests returned to higher latitudes, the rules had changed, and the planet now oscillated between cold and slightly less cold, rather than between warm and cool, a distinction that would matter enormously for life. Understanding why this happened 3 million years ago and not 10 million years earlier or later is the key to unlocking the story that unfolds through the rest of this narrative. What follows is not a tale of catastrophe, but of inevitability built from countless small steps, where oceans adjusted their paths, winds shifted their strength, and ice learned how to survive summer after summer. By tracing these steps carefully, the suddenness of the change begins to dissolve, replaced by a clearer picture of how Earth quietly prepared itself for an age of ice. The journey begins by looking back at the world just before the freeze, when the signs were present but the outcome was not yet sealed, a world balanced delicately on the edge of a colder future. Before the Great Freeze truly began, Earth existed in a climatic state that now feels almost unreal when compared to the ice-dominated planet of later ages, a world where the poles were cold but not commanding, and where seasonal rhythms still held authority over long-term extremes. During the late Pliocene, roughly between 5 and 3 million years ago, global temperatures hovered only a few degrees warmer than today, enough to sustain forests far into northern latitudes and to keep vast regions of the planet free from permanent ice. This was a time when the contrast between seasons mattered more than the contrast between epochs, when winters came and went and the snow melted reliably each summer rather than accumulating into something enduring. Greenland, now buried beneath kilometers of ice, was then a patchwork of tundra, shrubs, and boreal forest, its surface shaped more by rivers than by glaciers. Fossil pollen and plant remains preserved in sediments reveal species that today survive thousands of kilometers farther south, implying summers warm enough to support growing seasons long incompatible with modern Greenland. The Arctic Ocean itself was often seasonally ice-free, absorbing sunlight during summer months and releasing heat back into the atmosphere, a process that softened winters and discouraged the long-term survival of ice. Across North America and Eurasia, mountain glaciers existed but behaved politely, advancing during colder periods and retreating during warmer ones without ever spreading across entire continents. Sea levels during this time were significantly higher than today, sometimes by more than 10 meters, reflecting the absence of massive ice sheets in the Northern Hemisphere. Coastlines lay farther inland, shallow seas flooded continental shelves, and ocean currents flowed through passages that would later be exposed by falling seas, subtly redistributing heat around the globe. This relatively mild world was stabilized by a climate system that, while dynamic, remained resilient against runaway cooling. When ice formed during cooler phases, it reflected sunlight and encouraged further cooling, but summers were still warm enough to erase much of that ice before it could establish a permanent presence. The balance between snowfall and melting consistently favored retreat, preventing ice from learning the crucial lesson of persistence. Atmospheric carbon dioxide levels during this period were higher than those that would follow, commonly estimated between 350 and 450 parts per million, enough to trap additional heat and keep global temperatures elevated. This greenhouse blanket did not eliminate cold climates, but it softened their impact, ensuring that even extended cool intervals rarely crossed thresholds required for continent-scale glaciation. The climate oscillated, but it oscillated within a narrower and more forgiving range. Ocean circulation played a central role in maintaining this balance, carrying warm water toward the poles and exporting cold water back toward the equator. These currents acted like planetary arteries, preventing heat from stagnating in the tropics and starvation from settling in polar regions. As long as this circulation remained strong and coherent, ice faced an uphill struggle against summer melting. Yet within this seemingly stable system, signs of vulnerability were already present, faint but growing clearer with time. Seasonal contrasts were slowly weakening in some regions, with cooler summers failing to erase winter snowfall as efficiently as before. Snow lingered longer at higher elevations and higher latitudes, subtly increasing the reflective surface of the planet and nudging temperatures downward. At the same time, weather patterns were becoming more variable, with longer dry spells in some regions and heavier snowfall in others, creating pockets where ice had a better chance to survive. These changes were not dramatic enough to alarm the planet into an immediate transformation, but they were sufficient to begin stressing the old equilibrium. Like a bridge designed for lighter loads, Earth's pre-freeze climate could tolerate fluctuations, but not indefinitely. What makes this period so important is that it demonstrates the absence of any single dramatic trigger, no single winter that refused to end, or summer that failed catastrophically. Instead, the climate drifted gradually, each shift small enough to seem reversible, yet collectively steering the planet closer to a new regime. By the time the true onset of mega ice ages arrived, the conditions that once protected Earth from deep freezing had already been quietly eroded. This world before the freeze was not doomed, but it was delicately balanced, and balance in nature often depends on continued motion rather than stillness. As long as warmth flowed north, carbon dioxide lingered in the air, and summers retained their strength, ice remained a seasonal guest rather than a permanent resident. The next chapters trace how that balance was slowly, almost gently, tipped, transforming a flexible climate into one capable of sustaining ice for tens of thousands of years at a time. The quiet trap that Earth began to fall into was not forged on the surface, but traced invisibly through space, written into the slow geometry of the planet's path around the Sun, where tiny changes in orbit and tilt accumulated consequences far larger than their gentle motions suggested. Earth never travels around the Sun in a perfect circle, nor does it hold its axis rigid, and these variations, repeating over tens of thousands of years, have always paced the coming and going of ice. Yet around 3 million years ago, those familiar cycles began to interact with a climate system already losing its resilience. What had once been harmless fluctuations became decisive nudges, pushing summer warmth just low enough, just often enough, for snow to linger where it once vanished. The first piece of this orbital story lies in eccentricity, the slow stretching and tightening of Earth's orbit over roughly 100,000-year cycles. When eccentricity increases, the difference between Earth's closest and farthest distance from the Sun grows slightly, altering how solar energy is distributed across the year. On its own, this effect is modest, but it shapes how strongly the other orbital rhythms can influence climate, acting less like a driver and more like an amplifier. More critical for the onset of mega ice ages was obliquity, the tilt of Earth's axis, which controls how intense the seasons become. Higher tilt produces stronger seasonal contrasts, warmer summers, and colder winters, while lower tilt softens those differences, cooling summers and warming winters slightly. Around the time Earth began slipping toward sustained glaciation, obliquity cycles frequently aligned with lower tilt phases, weakening summers at high latitudes where ice is most vulnerable to melting. Precession added another layer, slowly shifting the timing of seasons relative to Earth's position along its orbit. This wobble determines whether a hemisphere's summer occurs when Earth is closer to or farther from the Sun, subtly adjusting seasonal intensity. When northern summers coincided with periods of reduced solar input, melting seasons shortened, allowing snowfields to survive just a bit longer year after year. What made these orbital shifts unusually powerful was not their magnitude, but their timing. They arrived when atmospheric carbon dioxide was already trending downward, oceans were redistributing heat less efficiently, and ice sheets were beginning to experiment with persistence. In this weakened climate state, small reductions in summer sunlight no longer bounced harmlessly off the system. Instead, they accumulated like unpaid debts. Once snow survived a single summer in critical regions, feedbacks quickly multiplied its influence. Snow and ice reflect far more sunlight than soil, rock, or vegetation, cooling the surface beneath and reinforcing the conditions that allowed them to survive in the first place. Each surviving patch became a local refrigerator, lowering temperatures nearby and encouraging further accumulation the following winter. Over multiple orbital cycles, this process transformed what had been rare anomalies into recurring features. Ice did not advance smoothly or uniformly, but in pulses, growing during particularly favorable alignments of tilt and precession, then retreating partially during warmer intervals. The key difference was that retreat never fully erased what had formed, leaving behind a memory of ice that made future growth easier. This gradual locking in of ice was not obvious from any single cycle, which is why it took thousands of years for the new pattern to become established. Early glacial advances were modest, confined to high elevations in polar regions, but they altered atmospheric circulation enough to weaken summer warmth even further. By the time large ice sheets began spreading across northern continents, the orbital trap had already closed. Importantly, these orbital changes did not force Earth into ice ages by sheer strength, but by rhythm. The repetition of slightly cooler summers again and again taught the climate system a new habit, one in which ice no longer needed extreme cold to survive. The planet learned how to stay cold. This lesson explains why the onset of mega ice ages feels abrupt in geological records, even though the underlying causes were slow. Once thresholds were crossed, ice growth accelerated and landscapes began changing faster than before. Rivers rerouted, soils froze, and ecosystems reorganized, responding not to a single cold year but to a new expectation of long-term instability. As Earth's orbit continued its endless cycles, the climate no longer returned to its earlier state of easy recovery. The same orbital patterns that once produced mild glacial episodes now drove massive expansions of ice. From this point forward, Earth's relationship with the Sun followed familiar rules, but the outcomes were irrevocably altered, setting the stage for the deeper transformations that followed. As Earth's orbit quietly weakened summer warmth, the oceans responded not with sudden drama, but with a slow reconsideration of how they moved heat around the planet, and this reorganization would prove just as important as changes in sunlight. The oceans store far more heat than the atmosphere, and for millions of years they had acted as Earth's great stabilizers, absorbing excess warmth in the tropics and releasing it toward the poles, smoothing temperature extremes and frustrating the long-term survival of ice. Around 3 million years ago, however, that stabilizing role began to falter, not because the oceans stopped moving, but because they began moving differently. One of the most significant shifts occurred in the global conveyor of deep and surface currents that link all major oceans into a single system. Small changes in salinity and temperature can dramatically alter where dense water sinks and where lighter water rises, redirecting entire circulation patterns. As high-latitude regions cooled and freshwater input from snow and ice increased, the delicate balance that powered warm currents toward the north weakened. In the North Atlantic, surface waters that once carried substantial warmth into polar regions began to cool before they could deliver their full heat load. Cooler, fresher water is less likely to sink, and sinking is the engine that pulls warm surface water northward. As this engine lost strength, northern latitudes received less imported warmth, allowing winter cold to linger deeper into spring and summer. At the same time, the closure and narrowing of ancient seaways altered how oceans exchanged heat between hemispheres. Shallow connections that once allowed warm water to spill freely between basins were gradually restricted by tectonic movement and falling sea levels. These barriers did not block circulation entirely, but they redirected it, favoring more isolated and regionally focused patterns. The Southern Ocean also played a critical role, acting as a gatekeeper between Antarctica and the rest of the world's oceans. As winds around Antarctica intensified and shifted slightly, they encouraged stronger upwelling of cold, deep water to the surface. This process released stored carbon dioxide into the atmosphere initially, but over longer timescales it enhanced the ocean's ability to absorb CO2, reinforcing global cooling. Colder surface waters absorbed more carbon dioxide, and as the oceans cooled, they quietly drew greenhouse gases out of the air. This chemical exchange did not happen overnight, but across tens of thousands of years, it shaved enough warmth from the atmosphere to matter. The cooling of the oceans and the cooling of the air became partners in the same slow descent. Another subtle change involved sea ice, which began to persist longer during summers in polar regions. Sea ice acts as a lid, limiting heat exchange between ocean and atmosphere and reflecting sunlight back into space. As seasonal sea ice lasted longer, it reduced the ocean's ability to release stored warmth during critical melting periods. This feedback loop transformed the oceans from defenders against ice into reluctant allies of its expansion. Each year that currents delivered slightly less heat northward, ice gained a small advantage. Over many cycles, those advantages accumulated, making ice survival less dependent on extreme cold and more on routine seasonal weakness. Importantly, none of these changes shut down ocean circulation entirely. The system continued to function, but in a diminished mode, like a heart still beating but no longer supplying the body with the same vigor. That reduction was enough to tip the balance at high latitudes, where the difference between melting and persistence often hinges on a single degree. As ice sheets began to grow larger, they further altered ocean circulation by adding fresh water and changing wind patterns above them. This created a reinforcing loop in which ice growth weakened circulation, and weaker circulation encouraged further ice growth. By the time this loop became established, reversing it would have required far more warming than Earth could muster under its new conditions. Through these quiet rearrangements, the oceans helped seal Earth's fate, ensuring that cooling episodes would no longer be brief visitors, but long-term residents. Heat that once flowed generously toward the poles now lingered closer to the equator, leaving high latitudes increasingly isolated. The stage was set for ice to move from experiment to permanence, a transition that would soon become unmistakable. With weakened summers and a less generous ocean, ice finally encountered conditions that allowed it to do something new, something it had rarely achieved before in the Northern Hemisphere: survive, spread, and remember itself from one year to the next. The rise of permanent ice sheets did not begin as a dramatic invasion of continents, but as a subtle experiment conducted by climate, testing whether snow could persist just long enough to change the rules. Around 3 million years ago, that experiment succeeded. The earliest signs appeared in high northern latitudes, particularly across Greenland and parts of northeastern North America, where winter snowfall began to exceed summer melting on a regular basis. At first, the imbalance was small, almost trivial, measured in centimeters rather than meters, but persistence mattered more than volume. Once snow survived a summer, it compacted into firn, and firn into ice, locking away cold from previous seasons like a memory stored in crystal. As ice thickened, its surface rose higher into the atmosphere, where temperatures are naturally colder. This elevation feedback meant that every additional meter of ice made the surface slightly less likely to melt, even if conditions below remained marginal. Ice sheets were no longer just passive responses to climate. They were becoming active architects of their own survival. The Northern Hemisphere had long lacked large, stable ice sheets, not because it could not get cold, but because it could not stay cold. Antarctica had crossed that threshold tens of millions of years earlier, isolated by ocean currents and positioned squarely over the pole. Now, for the first time, northern continents began to flirt seriously with the same fate. Greenland marked a critical turning point. Once ice there reached sufficient thickness and spatial extent, it stopped behaving like a seasonal feature and began acting like a permanent fixture. Sediment records indicate a rapid increase in ice-rafted debris entering surrounding seas, clear evidence that glaciers were reaching the coast and calving icebergs into the ocean. In North America, ice advanced more cautiously, initially confined to highlands and northern interiors. Yet each glacial advance reshaped the land beneath it, scraping away soil, flattening relief, and creating smoother surfaces that favored future ice spread. The continent was slowly being prepared, carved into a landscape more compatible with glaciation. Ice sheets also began influencing atmospheric circulation in profound ways. Their bright surfaces reflected sunlight, cooling the air above them and strengthening temperature contrasts between ice-covered regions and lower latitudes. These contrasts altered wind patterns, steering storms along new paths that delivered more snowfall to glaciated areas, reinforcing growth. At the same time, ice sheets acted as barriers, deflecting air masses and redirecting moisture. Regions downwind of ice became drier and colder, while zones along their margins received heavy snowfall. This redistribution of precipitation further entrenched ice where it already existed. What made this phase decisive was not the size of early ice sheets, but their stability. Even during warmer intervals, melting failed to erase them completely. Residual ice lingered, ready to expand again when orbital conditions favored cooling, ensuring that each cold phase started from a higher baseline than the last. This marked a fundamental change in Earth's climate behavior. Previously, glacial episodes were largely symmetrical, advancing and retreating in response to orbital forcing. Now, retreat was incomplete, and advance became progressively easier, allowing ice sheets to grow larger over successive cycles. Sea levels responded accordingly, falling as increasing volumes of water were locked away on land. Shorelines migrated seaward, exposing continental shelves and altering ocean circulation further. These changes fed back into climate, tightening the grip of ice on the planet. By the time large, coherent ice sheets were firmly established, Earth had crossed a point of no easy return. The presence of permanent northern ice transformed temporary cooling into a persistent state, one that could only be interrupted, not undone. From this moment onward, ice was no longer an occasional guest but a dominant force in Earth's climate system. While ice sheets were learning how to persist, an even quieter change was unfolding in the background, one that never announced itself with storms or advancing glaciers, yet steadily removed the invisible insulation that had long protected Earth from deep cold. Atmospheric carbon dioxide, the planet's most influential long-term greenhouse gas, was declining, not abruptly, but with a patience that matched the slow rhythms of climate itself. By the time mega ice ages began to dominate Earth's behavior, this decline had crossed a threshold that made recovery increasingly difficult. For much of the earlier Pliocene, carbon dioxide levels remained high enough to soften the extremes imposed by orbital cycles. Even when summers weakened slightly, enough heat lingered in the atmosphere to erase most winter snow. As CO2 concentrations drifted downward over hundreds of thousands of years, that buffering capacity weakened, leaving climate more exposed to seasonal variations. The causes of this decline were not dramatic, but they were persistent. Chemical weathering of rocks, especially as mountain ranges rose and erosion accelerated, consumed carbon dioxide as rainwater reacted with exposed minerals. Each reaction removed a tiny fraction of CO2 from the air, locking it away in ocean sediments as carbonate minerals, a process invisible in any single year but powerful across geological time. Cooling oceans amplified this effect. Colder water can dissolve more carbon dioxide, and as global temperatures fell, the oceans quietly absorbed additional CO2 from the atmosphere. This exchange further reduced greenhouse warming, reinforcing cooling and creating a feedback loop that favored ice. Biological activity also played a role, as changes in ocean circulation altered nutrient delivery and marine productivity. Phytoplankton growth increased in some regions, drawing carbon from the surface ocean and exporting it to the deep sea when organisms died and sank. Over long timescales, this biological pump helped sequester carbon away from the atmosphere. What makes carbon dioxide so influential is not its dramatic swings, but its ability to set the baseline upon which all other climate forces operate. Orbital changes dictate when and where sunlight arrives, but CO2 determines how much of that energy is retained. As concentrations declined, summers that once melted ice efficiently began failing more often. This shift did not plunge Earth instantly into deep freeze. Instead, it altered probabilities, making glacial growth more likely during favorable orbital alignments and retreat less complete during warmer phases. Each glacial cycle shaved a little more carbon from the atmosphere, nudging the system further toward cold. By roughly 3 million years ago, estimates suggest atmospheric carbon dioxide had fallen into a range where permanent ice sheets could exist in the Northern Hemisphere. At this point, the climate system behaved differently even under familiar orbital patterns. What once produced modest cooling now generated substantial glaciation. The importance of this slow decline lies in how irreversible it became on human timescales. Carbon removed through weathering and deep ocean storage does not return quickly, requiring tectonic or volcanic processes operating over millions of years. As a result, once CO2 dropped below certain levels, Earth lost an easy escape route from its icy state. This helps explain why later warm intervals, though significant, never fully restored the pre-freeze world. Even when ice retreated, greenhouse warming was insufficient to eliminate it entirely. The planet oscillated between cold and less cold, trapped by a baseline that had shifted downward. Carbon dioxide's role in the onset of mega ice ages illustrates a broader truth about Earth's climate. The most powerful changes often arise not from sudden shocks, but from long-term imbalances that quietly accumulate. By the time their effects become obvious, the system has already moved beyond the point where simple reversal is possible. As ice sheets expanded and carbon dioxide declined together, Earth's climate acquired a new stability, one defined by cold rather than warmth. This stability was deceptive, however, because it masked the growing influence of other forces still reshaping the planet. Among them were mountains, rising slowly but insistently, altering winds, rainfall, and the very pathways through which climate expressed itself. As carbon dioxide declined and ice learned how to persist, the solid surface of the planet was also changing in ways that quietly rewrote the rules of climate, because mountains do not merely rise into the sky, they reach outward into the atmosphere and redirect the flow of air and water across entire continents. During the millions of years leading up to the onset of mega ice ages, several major mountain systems continued to grow taller and broader, their uplift slow enough to escape notice in human imagination, yet powerful enough to alter global climate trajectories. These rising barriers reshaped winds, intensified weathering, and redistributed rainfall, creating conditions that increasingly favored cooling. As mountains rise, they force air to ascend, cooling it and causing moisture to fall as rain or snow on windward slopes. This process strips moisture from air masses before they reach interior regions, leaving large areas downwind drier and more prone to temperature extremes. In a cooling world, this drying effect mattered enormously, because dry air allows snow to persist longer by limiting summer cloud cover that might otherwise trap heat. The uplift of large plateaus and ranges also accelerated chemical weathering, exposing fresh rock surfaces to rain and atmospheric carbon dioxide. Each exposed mineral face acted as a tiny carbon sink, reacting with CO2 and transporting it via rivers to the oceans, where it was locked away in sediments. Over millions of years, this steady drawdown contributed to the long-term decline in greenhouse gases that made ice ages possible. Mountain ranges further altered atmospheric circulation by steering prevailing winds into new paths. Jet streams bent and shifted, guiding storm tracks differently across continents. Regions that once received regular warmth and moisture found themselves increasingly isolated, while others experienced heavier snowfall that fed growing ice sheets. In high latitudes, these effects compounded existing cooling. Mountains created elevated cold zones where snow could survive even marginal summers, acting as seed points for glaciation. Once established, these high-altitude ice masses expanded outward and downward, linking with other ice-covered regions and accelerating continental glaciation. The timing of these tectonic changes mattered as much as their magnitude. Had major uplifts occurred when carbon dioxide levels were high and oceans were transporting heat efficiently, their climatic impact would have been muted. Instead, they rose into a world already losing warmth, amplifying cooling rather than counteracting it. Mountains also influenced monsoon systems and large-scale precipitation patterns, redistributing fresh water in ways that affected ocean salinity. Changes in river discharge altered where dense water formed in the oceans, subtly weakening heat-transporting currents. This connection between rock uplift and ocean circulation linked solid Earth processes directly to the persistence of ice. The cumulative effect was a planet increasingly compartmentalized, with climatic zones separated by physical barriers that reduced mixing and moderation. Warm air struggled to reach polar regions, and cold air lingered longer over ice-covered interiors. Seasonal contrasts sharpened in some places and weakened in others, but overall, the system tilted toward instability. What makes mountain uplift such a powerful climate force is its permanence. Unlike orbital variations, which cycle predictably, mountains do not lower themselves once raised. Their influence persists, continuing to steer winds and weather long after the initial uplift has ended. By the time mega ice ages were firmly established, Earth's topography had become an accomplice in their maintenance. Rising ranges did not cause ice ages on their own, but they ensured that once ice began to grow, it encountered fewer obstacles and more support. The planet's surface had been quietly rearranged to favor cold. This convergence of slow forces reveals why the shift into mega ice ages was so durable. Ice was no longer fighting against geography, chemistry, and circulation, but advancing with their help. With mountains guiding the atmosphere and erosion stripping warmth from the air, Earth entered a new climatic chapter, one governed by a harsher rhythm that would soon become unmistakable. By the time mountains had reshaped winds and carbon dioxide had slipped to lower ground, Earth's climate crossed into something more than cold. It entered a new rhythm, a repeating pattern of advance and retreat that was slower, heavier, and far more unforgiving than anything that came before. Ice ages had existed earlier in Earth's history, but now they followed a different beat, one that stretched time itself, extending glacial periods and compressing warmer intervals into brief pauses rather than true recoveries. This was the moment when climate stopped oscillating lightly and began swinging with mass and momentum. The defining feature of this new rhythm was not constant cold, but persistence. Glacial phases now lasted tens of thousands of years longer than earlier cycles, allowing ice sheets to grow thicker, broader, and more influential. Warm periods still arrived, but they were shorter and weaker, often failing to erase the ice entirely before the next cooling phase began. This change is visible in deep-sea sediments, where oxygen isotopes record the waxing and waning of global ice volume. Before this transition, isotope variations show relatively modest swings, reflecting smaller ice sheets and more symmetrical cycles. Afterward, the signal deepens and stretches, revealing longer, more extreme glaciations punctuated by brief interludes of partial thaw. What locked Earth into this rhythm was the growing inertia of ice itself. Large ice sheets respond slowly to warming, requiring prolonged heat to melt fully, while they respond efficiently to cooling, expanding rapidly when temperatures fall. This asymmetry meant that once ice grew beyond a certain size, it dominated the timing of climate change rather than merely following it. Orbital cycles still set the tempo, but the music had changed. The same variations in tilt and precession that once produced mild glacial advances now triggered massive expansions of ice. Eccentricity, previously a background influence, became more visible as ice sheets amplified its subtle effects, stretching cycles into longer, deeper cold phases. This new rhythm also altered how the atmosphere behaved over time. Extended glaciations strengthened polar high-pressure systems and shifted storm tracks toward lower latitudes. Dry, cold air spread across continents, while winds intensified along the edges of ice sheets, feeding snowfall where it mattered most. As ice advanced and retreated repeatedly, landscapes adjusted to the beat. Soils thinned or vanished, rivers changed course, and erosion accelerated during melt phases, transporting vast amounts of sediment to the oceans. Each cycle left the land smoother and more uniform, making future ice advances easier and faster. The oceans, too, adapted to the rhythm. Long glacial periods lowered sea levels dramatically, altering coastlines and restricting shallow seaways. These changes further modified circulation patterns, reinforcing the same climate state that produced them. What makes this rhythm so significant is that it created predictability without stability. Earth's climate became more regular in its cycling, yet more extreme in its outcomes. Life could anticipate change, but it could not rely on gentleness. By locking into this pattern, Earth committed to a future of repeated stress, where ecosystems would be forced to adapt again and again to shifting conditions. The planet had not frozen solid, but it had accepted ice as a recurring architect of its surface and climate. From this point forward, the question was no longer whether ice would return, but how much would come back each time. This rhythm echoed through millions of years, shaping continents and oceans alike, and it formed the environmental backdrop against which many species would struggle, migrate, or disappear. The world had learned a new habit, and habits, once formed at planetary scale, are difficult to break. Under this relentless pulse of ice and time, the stage was set for landscapes to be ground down and for life to face challenges unlike any it had known before. As the new rhythm of ice settled into Earth's climate, the land itself became the canvas upon which this slow violence was repeatedly written, each glacial advance pressing down with enormous weight, each retreat peeling the surface away layer by layer. Continents that had once been shaped primarily by rivers and weather now found themselves under the grip of moving ice, a force indifferent to delicacy, capable of flattening mountains, damming valleys, and erasing landscapes that had taken millions of years to form. The pressure was relentless, not because it was constant, but because it returned again and again, allowing little time for recovery. When ice sheets advanced, they did not simply rest upon the land, they flowed, driven by their own mass, dragging rock fragments frozen into their bases like sandpaper across the surface below. Bedrock was scraped smooth, hills were truncated, and valleys were widened into broad U-shaped forms that still scar northern continents today. Soils that had accumulated slowly under forests were stripped away in a single glacial cycle, exposing fresh rock and resetting ecological clocks to zero. Rivers responded to this pressure by surrendering their old courses. Glaciers dammed valleys, forcing meltwater to find new paths, sometimes carving immense spillways in sudden catastrophic releases during warmer phases. As ice retreated, rivers inherited landscapes profoundly altered, flowing through over-deepened basins and across plains littered with glacial debris. Repeated glaciations amplified these changes. Each advance smoothed the land further, removing obstacles that might have slowed the next ice sheet. In this way, the landscape itself learned how to be glaciated, becoming more compatible with ice over time. The weight of ice also depressed the crust beneath it, pushing continents downward by hundreds of meters. This subsidence altered local sea levels and drainage patterns, trapping water in inland basins and reshaping coastlines. When ice melted, the land rebounded slowly, lifting former seabeds into terraces and leaving raised beaches as quiet records of ancient ice. Along continental margins, falling sea levels exposed vast shelves, transforming shallow seas into broad plains. These newly exposed lands changed atmospheric circulation, creating larger landmasses that heated and cooled more rapidly than water. The contrast intensified seasonal extremes and fed back into the glacial system that produced it. Sediment poured into the oceans during melt phases, carried by swollen rivers and collapsing ice fronts. These sediments altered marine ecosystems, buried habitats, and recorded the pulse of ice in layered deposits on the seafloor. Each layer told a story of advance and retreat, pressure and release. For life on land, this pressure meant constant displacement. Plants retreated southward or vanished, animals followed shifting habitats, and entire ecosystems migrated in rhythm with the ice. Regions repeatedly overridden by glaciers became biological blank slates, recolonized anew after each retreat. Yet even areas beyond the ice felt its influence. Cold winds blowing off ice sheets dried surrounding lands, expanding deserts and grasslands. Dust carried by these winds darkened snow surfaces elsewhere, sometimes accelerating melting, sometimes cooling the atmosphere by blocking sunlight. The landscapes born of this era were harsher, simpler, and more unstable than those that came before. Complex soils gave way to thin coverings, and long, uninterrupted ecological histories were replaced by repeated resets. Earth's surface became a place shaped by endurance rather than accumulation. This relentless pressure did more than change scenery. It altered the tempo of natural processes. Erosion accelerated, sedimentation increased, and the pace of geological change quickened under the influence of ice. The planet itself seemed to breathe more deeply, inhaling cold and exhaling meltwater in long, heavy cycles. Under this pressure, the land ceased to be a passive stage and became an active participant in the Ice Age story. Each scar left by ice influenced how the next advance unfolded, creating a feedback between climate and terrain. The world was being sculpted into a form that would remember ice long after it retreated, ensuring that its influence would persist far beyond any single glacial cycle. As landscapes were reshaped and pressure mounted, life across the planet found itself living under rules that had quietly but decisively changed. Because the onset of mega ice ages did not merely cool the world, it made it unstable, demanding flexibility, movement, and endurance from every species caught within its reach. The long, grinding cycles of ice advance and retreat fragmented habitats, turning once continuous ecosystems into shifting mosaics that expanded, contracted, and disappeared with the climate's pulse. Survival was no longer about thriving in one place, but about adapting to constant change. Plants were often the first to feel the strain. Forests that had stretched across northern latitudes retreated southward as temperatures dropped and growing seasons shortened. In their place came open grasslands, tundra, and sparse shrublands, ecosystems better suited to cold and dryness, but far less stable over time. Each glacial advance pushed these plant communities farther toward the equator or into isolated refuges, pockets of relative warmth protected by geography or ocean influence. When ice retreated, forests advanced again, but rarely to their former extent or composition. Species assemblages shifted, mixing in new combinations that reflected survival rather than historical continuity. Animals responded by moving, evolving, or disappearing. Large mammals followed the shifting edges of vegetation, migrating across newly exposed land bridges during periods of low sea level. These migrations connected continents intermittently, allowing species to spread, compete, and sometimes replace one another in ways impossible under stable climates. Cold favored certain traits, thicker insulation, larger body sizes, and seasonal behaviors tuned to scarcity. Species unable to adapt quickly enough found themselves squeezed between advancing ice and deteriorating habitats to the south. Extinction during this period was not always sudden, but it was persistent, claiming lineages gradually as conditions repeated their stresses again and again. Marine life also felt the cold, though in different ways. Changing ocean circulation altered nutrient distribution, reshaping food webs from the surface to the deep sea. Some regions became highly productive, while others starved, forcing marine species to track shifting zones of abundance. Plankton communities changed composition, influencing everything above them in the food chain. As certain species thrived in colder, nutrient-rich waters, others declined, altering the biological pump that moved carbon through the oceans. These biological shifts fed back into climate, subtly influencing carbon storage and atmospheric composition. One of the most important consequences of this climatic instability was increased environmental variability. Rather than facing a single long cold period, organisms endured repeated transitions from cold to warm and back again, each time at a slightly different intensity. Adaptation required flexibility, not specialization, favoring species capable of exploiting a wide range of conditions. This pressure reshaped evolutionary pathways. Traits that allowed rapid dispersal, broad diets, or seasonal behaviors became more valuable than those optimized for narrow ecological niches. Life increasingly rewarded resilience over efficiency. Importantly, these changes unfolded unevenly across the globe. Regions closer to the equator experienced less direct glaciation, but still suffered from altered rainfall patterns and temperature swings. In these areas, instability rather than cold itself became the dominant challenge, disrupting ecosystems that had previously been relatively predictable. Over time, this selective pressure produced ecosystems that were leaner and more dynamic. Species interactions became more fluid, with ranges expanding and contracting repeatedly. The natural world adjusted not by settling into a new balance, but by learning to live without one. The onset of mega ice ages thus acted as a global filter, testing life's capacity to endure long-term uncertainty. Those that passed the test reshaped the biosphere that followed, while those that failed left only traces in the fossil record. Under the long shadow of ice, life did not simply survive. It transformed, setting the stage for future evolutionary experiments that would unfold in an increasingly restless world. While ice sheets dominated the far north, their influence reached deep into Africa, a continent never buried beneath continental glaciers, yet profoundly reshaped by the same planetary forces that drove Earth into mega ice ages. Global cooling altered atmospheric circulation patterns that governed rainfall across Africa, turning once reliable climate rhythms into erratic swings between wet and dry. The result was not a steady descent into cold, but a continent pulled between extremes where stability became rare and unpredictability the norm. Before this shift, much of Africa experienced relatively consistent climate zones, with long-standing forests, woodlands, and grasslands arranged in broad, persistent belts. As ice ages intensified in the Northern Hemisphere, these belts began to fracture. Monsoon systems weakened or shifted position, changing where and when rain fell, sometimes dramatically within a few thousand years. Periods of global cooling tended to dry large parts of Africa, shrinking lakes and rivers and converting forests into open savannas. During warmer interludes, rainfall returned, lakes expanded, and vegetation rebounded, but rarely to its former extent or in the same configuration. This repeated expansion and collapse created a landscape in constant flux. One of the clearest signs of this instability appears in the geological record of ancient lakes. Sediment cores reveal cycles of deep freshwater conditions followed by prolonged droughts, sometimes occurring multiple times within a single glacial cycle. These fluctuations were tied not to local events, but to distant ice sheets altering global wind and temperature patterns. As ice grew in the north, it strengthened high-pressure systems that pushed dry air southward. At the same time, cooler global temperatures reduced evaporation from the oceans, limiting the moisture available to fuel rainfall over land. Africa, dependent on seasonal rains, felt these changes acutely. Vegetation responded quickly. Forests retreated into isolated refuges along coasts and highlands, while grasslands expanded across regions once shaded by trees. This transformation did not happen once, but repeatedly, forcing ecosystems to reorganize again and again. Animals followed the shifting landscapes. Species adapted to woodland habitats found themselves compressed into shrinking patches, while those suited to open environments spread widely during drier phases. Migration became a necessity rather than an option, reshaping patterns of competition and survival. The instability of African climate during this period is critical because it created a setting unlike that of most other continents. Rather than long, continuous glaciation or steady warmth, Africa experienced rapid alternation, sometimes within time frames short enough to influence evolutionary pressures directly. This made flexibility and behavioral adaptation especially valuable. River systems also became unreliable. Major waterways expanded during wet phases and fragmented or vanished during dry ones, breaking connections between habitats. Access to water, once predictable, became uncertain, adding another layer of stress to life on the continent. Importantly, these changes were not uniformly negative. Periods of expansion created new ecological opportunities, allowing species to spread into regions previously unavailable. However, each opportunity was temporary, and success depended on the ability to cope with eventual collapse. Africa's climate instability did not result from local forces alone. It was the distant echo of ice forming thousands of kilometers away, proof that mega ice ages reshaped the entire planet, not just frozen regions. The continent became a testing ground where adaptability determined survival. This volatile environment laid crucial groundwork for later evolutionary developments. Repeated exposure to shifting climates favored organisms capable of rapid response, mobility, and innovation. Africa was being shaped into a landscape where change itself became the defining constant, preparing it for events yet to come. Within this restless African landscape, the human line felt the pressure of mega ice, ages indirectly but persistently, shaped not by walls of ice, but by the instability those ice sheets imposed on distant climates that governed food, water, and survival. Early hominins did not face advancing glaciers, yet their world was repeatedly rearranged, forcing them to adapt to environments that shifted within the span of many generations, rather than across unchanging epochs. The onset of mega ice ages transformed human evolution into a dialogue with uncertainty. As forests fragmented and grasslands expanded during cooler, drier phases, hominin habitats became more open and less predictable. Tree cover that once offered shelter and reliable food sources retreated into scattered refuges, while wide savannas exposed early humans to new dangers and opportunities. Navigating these landscapes demanded greater mobility, awareness, and cooperation. Dietary pressures intensified under this instability. Seasonal shortages became more common as plant foods fluctuated with rainfall, pushing hominins toward broader, more flexible diets. Scavenging and opportunistic hunting grew more important, encouraging behaviors that favored planning, tool use, and social coordination. Water scarcity during dry phases shaped movement patterns. Populations clustered around shrinking lakes and rivers, increasing competition and social interaction. When wetter periods returned, these same groups expanded outward, carrying knowledge and behaviors refined under pressure. This repeated contraction and expansion acted as a powerful evolutionary filter. Traits that supported survival across varied environments were favored, while those dependent on narrow ecological conditions became liabilities. Flexibility, both behavioral and physiological, became a defining advantage. Climate instability also influenced body and brain evolution indirectly. Navigating complex social environments, remembering distant resources, and anticipating seasonal changes rewarded cognitive abilities. While brain growth was not caused by cold itself, the challenges imposed by fluctuating climates made enhanced problem-solving increasingly valuable. Tool traditions likely became more important during this time, not simply as hunting aids, but as tools for coping with unpredictability. Processing varied foods, accessing new resources, and defending against predators all benefited from technological solutions that could be modified as conditions changed. Innovation was no longer optional, it was survival. Social bonds deepened under repeated stress. Cooperation improved access to food and protection, while shared knowledge helped groups respond to environmental shifts. Those able to maintain social cohesion during hard times were better positioned to exploit favorable conditions when they returned. Importantly, these pressures did not act in one direction or at one pace. Different regions of Africa experienced climate swings differently, creating a mosaic of selective environments. This diversity helped prevent a single evolutionary path from dominating too quickly, maintaining variation within the human line. Migration patterns were influenced as well. Shifting habitats opened and closed corridors across the continent, occasionally connecting populations that had been isolated. These encounters allowed genetic and cultural exchange, spreading adaptive traits more widely. The influence of mega ice ages thus reached into human ancestry not as a single dramatic turning point, but as a prolonged background force. Each climatic swing tested the same populations again and again, reinforcing the value of adaptability. Over time, this repetition shaped a lineage increasingly capable of responding to change. What distinguishes this phase of human evolution is not the emergence of a specific trait, but the sharpening of a strategy. Survival favored those who could endure uncertainty, learn quickly, and adjust behavior without waiting for biological change. The human line began leaning more heavily on culture and learning as tools of survival. Under the long shadow of ice forming far to the north, early humans were molded by absence rather than presence, by missing rains, shifting food webs, and unreliable landscapes. The cold did not touch them directly, yet it reached them through winds, clouds, and seasons that no longer followed old rules. In this way, mega ice ages quietly guided human evolution, preparing a lineage that would one day prove uniquely capable of thriving in a world defined by change. As scientists pieced together this long descent into cold, many early explanations reached instinctively for drama, proposing sudden catastrophes, cosmic accidents, or singular disasters powerful enough to plunge Earth into mega ice ages in a geological instant. These ideas were appealing because they matched human expectations of cause and effect, where great changes demand great events, yet the deeper the evidence was examined, the more these explanations unraveled. The truth turned out to be quieter, slower, and in many ways more unsettling. One persistent myth held that a single massive volcanic episode dimmed the sun and froze the planet. While volcanic eruptions can cool climate temporarily by injecting aerosols into the atmosphere, their effects fade within years to decades. No volcanic record aligns with the sustained multi-million-year cooling required to explain the birth of permanent northern ice sheets. Another popular idea pointed to asteroid impacts, imagining a collision large enough to throw Earth into a long winter. Yet, impacts capable of global climatic disruption leave unmistakable geological fingerprints, layers rich in rare elements and shock features that persist worldwide. No such signal coincides with the gradual onset of mega ice ages, And even if one had occurred, its effects would have been fleeting compared to the enduring shift observed. Some explanations focused on sudden ocean shutdowns, envisioning an abrupt halt to heat-transporting currents. Modern observations show that ocean circulation can weaken or shift, but it does so gradually, constrained by physics and feedbacks. The geological record supports this slow adjustment, not a dramatic collapse, aligning with the broader picture of incremental change. There were also claims that ice ages began simply because Earth drifted farther from the Sun, or because solar output declined sharply. In reality, changes in solar energy over this time frame were minimal and insufficient to account for the scale of cooling observed. Earth's distance from the Sun and its luminosity remained essentially stable, eliminating these as primary drivers. What these myths share is a desire for simplicity, for a single cause that can be pointed to and blamed. Yet, Earth's climate does not operate under such rules, especially over millions of years. It responds instead to the accumulation of small imbalances, each reinforcing the next until a threshold is crossed. The evidence tells a different story, one in which multiple slow processes converged. Orbital variations weakened summers, carbon dioxide declined, oceans redistributed heat less efficiently, mountains reshaped winds, and ice learned how to persist. No single factor dominated, but together they created a new climate state. This realization reframes the idea of suddenness itself. The transition into mega ice ages appears abrupt in geological records because thresholds were crossed, not because causes arrived suddenly. Once crossed, feedbacks accelerated change, making the shift seem sharp despite its slow preparation. Understanding this distinction is crucial, because it reveals how easily Earth can appear stable right up until it is not. For long periods, the climate hovered near a tipping point, absorbing disturbances without dramatic response. Then, once conditions aligned, change unfolded rapidly relative to what came before. Old myths also underestimated the power of feedbacks. Ice reflects sunlight, cooling the surface and encouraging more ice. Cooler oceans absorb more carbon dioxide, reinforcing cooling. Altered winds redistribute snow to favor ice growth. These feedbacks transformed modest initial changes into lasting transformations. The abandonment of catastrophic explanations does not make the story less dramatic. Instead, it reveals a planet governed by patience, where persistence outweighs force. Earth did not need a single violent push, it needed time. This understanding also explains why the mega ice age state proved so resilient. Because it was built gradually from multiple reinforcing processes, dismantling it would require reversing all of them at once. Short-term warming events could interrupt glaciation, but they could not erase the underlying conditions. By letting go of old myths, the true nature of Earth's climate shift becomes clearer and more sobering. The planet is capable of transforming itself profoundly without fanfare, guided by small changes acting in concert. The ice ages were not an accident, but the outcome of a long negotiation between Earth systems. In recognizing this, the mystery of why Earth suddenly entered mega ice ages begins to dissolve. What remains is a deeper appreciation for how thresholds shape planetary behavior. Once crossed, they redefine what is possible, leaving behind a world that follows new rules long after the moment of transition has passed. Even after ice retreated during warmer intervals, Earth never truly returned to the gentler world that existed before 3 million years ago, because the conditions that once allowed warmth to dominate had quietly vanished. Interglacials came and went, sometimes lasting thousands of years, sometimes bringing forests back to higher latitudes. Yet beneath these surface recoveries, the deeper structure of climate remained altered. The ice had learned how to leave without forgetting how to return. One reason the ice never fully left was the lingering presence of large ice sheets themselves, which acted as anchors for cold. Even during warm phases, remnants of ice persisted in high latitudes and elevated regions, maintaining reflective surfaces that cooled surrounding air. These survivors shortened summers locally, ensuring that complete melting required more warmth than the climate could provide. Carbon dioxide levels also failed to rebound to earlier heights. While concentrations rose during interglacials, they remained below the levels typical of the pre-freeze world, limiting how much heat the atmosphere could trap. Without that greenhouse support, warmth arrived as a temporary guest rather than a permanent resident. Oceans, too, remembered the ice. Sea levels rose during warm periods, but did not always restore shallow seaways and coastal configurations to their former states. Altered coastlines and ocean gateways continued to influence circulation, preventing the full return of heat transport patterns that once softened polar climates. The land itself had been reshaped in ways that favored future glaciation. Smoother surfaces, stripped of thick soils and forests, reflected more sunlight and allowed ice to spread more easily when cooling resumed. Once prepared by repeated glaciations, continents no longer resisted ice as they once had. Another factor was timing. Warm intervals often coincided with orbital configurations that favored limited melting rather than maximum solar input. Even when summers strengthened, they rarely aligned perfectly with other conditions needed to erase ice completely, leaving behind a cold residue that primed the next advance. This persistence created an asymmetry in climate behavior. Cooling phases were effective and cumulative, while warming phases were partial and constrained. Earth oscillated within a narrowed range, never fully escaping the cold baseline established during the onset of mega ice ages. The psychological effect of this persistence, if Earth could be said to have one, was a loss of climatic memory of warmth. Each cycle began from a colder starting point than before, even if surface conditions appeared similar during brief interludes. Over time, this made deep glaciation the default rather than the exception. Life adapted accordingly. Species evolved strategies that assumed instability, migration, and periodic stress. Ecosystems rebuilt themselves after each glacial retreat with the expectation that ice would return, shaping resilience rather than permanence. The idea that Earth could simply go back to an earlier state proves misleading in this context. Climate systems, once shifted, carry momentum that resists reversal. The path into mega ice ages was gradual, but the path out would have required changes just as extensive and coordinated, changes that did not occur. This explains why later warm periods, including some warmer than today, failed to erase ice sheets entirely. They softened the climate, reshaped ecosystems, and raised sea levels, but they did not rewrite the rules established millions of years earlier. The underlying architecture of cold remained intact. The persistence of ice also altered how future climate changes would unfold. Every new cooling phase, built upon an inherited landscape and atmosphere already biased toward glaciation. The system became more sensitive to small perturbations, responding strongly to orbital shifts that once produced modest effects. In this way, Earth's failure to fully thaw was not a failure at all, but a consequence of how deeply the transition had been embedded. Mega ice ages were not a temporary episode, but a long-term mode of operation. Once entered, they shaped all subsequent climate behavior. This realization reframes the meaning of interglacials. They were not returns to normalcy, but brief respites within a colder world. Their warmth was relative, not absolute, and their limits were set by a climate system that no longer remembered how to sustain long-term heat. As the planet continued cycling through ice and thaw, the shadow of that ancient decision persisted. Earth had chosen a path where ice would always be waiting just beyond the edge of warmth. The final section draws this story together, reflecting on how that choice still governs the climate of the present day. The long shadow cast by Earth's decision 3 million years ago still stretches into the present, shaping coastlines, weather, ecosystems, and even the expectations humans hold about what climate is supposed to be. What feels normal today, a world capable of plunging into ice ages and emerging again, scarred but intact, is not Earth's default state, but the result of a slow commitment made by interacting systems that learned how to sustain cold. Once that commitment formed, every future climate event unfolded within its boundaries. The mega ice ages did more than cover continents with ice. They redefined Earth's sensitivity. Small changes in sunlight, greenhouse gases, or circulation now produce outsized responses compared to the pre-freeze world. The climate became less forgiving, quicker to amplify disturbances, and slower to recover from them. Sea levels rose and fell dramatically under this new regime, redrawing maps again and again. Coastal plains appeared and vanished, land bridges formed and disappeared, and oceans reshaped continental margins with each cycle. Human civilizations would later inherit shorelines and river systems already sculpted by these ancient rhythms. The atmosphere, too, carries this legacy. Patterns of wind and precipitation evolved in response to repeated glaciations, locking in behaviors that still influence storm tracks and climate zones today. The contrast between polar and tropical regions, sharpened by long-term ice, remains a defining feature of Earth's climate engine. Life adapted to this world of repetition and stress, favoring resilience over specialization. Ecosystems learned to rebuild, migrate, and reorganize, while extinctions thinned the tree of life, pruning branches unable to endure recurring disruption. The biosphere that surrounds us is, in many ways, a product of survival under Ice Age rules. For humans, the consequences were profound. Our species emerged into a world already conditioned by ice, instability, and rapid environmental change. The capacity to adapt culturally, to plan, cooperate, and innovate was nurtured in a climate that rarely offered long-term certainty. Understanding why Earth entered mega ice ages reframes how we think about climate itself. It reveals that stability is not guaranteed by gentleness, and that dramatic shifts do not always announce themselves with catastrophe. Often, they arrive quietly through persistence, alignment, and time. The story also carries a deeper lesson about thresholds. For millions of years, Earth hovered near a boundary, absorbing changes without obvious transformation. Then, once crossed, that boundary redefined everything that followed. This perspective dissolves the illusion that climate states are easily reversible. Earth did not stumble into ice ages by accident, and it cannot simply step out of them without equally profound, sustained changes. The climate remembers its past, carrying forward the consequences of long-gone conditions. As the planet continues its orbital dance, the same celestial rhythms still play above us. What has changed is how Earth responds to them, shaped by ice sheets, oceans, mountains, and atmospheric composition inherited from that ancient transition. The past is not behind us. It is embedded in the present. The mega ice ages remind us that Earth's most influential changes often emerge from patience rather than drama. They are the result of systems slowly aligning, reinforcing one another until a new normal takes hold. Once established, that normal governs everything that comes after. In the quiet unfolding of this story, there is no single villain and no single moment of loss. There is only a planet responding to its own physics, chemistry, and geometry, finding a configuration that endures. Ice became part of Earth's identity. As the narrative fades, the image that remains is not one of frozen catastrophe, but of a world breathing slowly through deep time, inhaling cold and exhaling warmth in cycles measured not in years, but in ages. The mega ice ages were not an interruption in Earth's story. They became its rhythm. And in that rhythm, still beating beneath our feet, the ancient choice continues to shape the world we call home.